An electric power system is a network of electrical components that supply, transfer, and utilize electric power. The electrical grid is a prime example of a power system, delivering power to homes and industries over a wide area. It consists of generators that produce power, a transmission system that transports power from generating centers to load centers, and a distribution system that distributes power to nearby homes and industries. To enhance control and management of power system operations, an energy management system, EMS, is employed at the control center of the power system. EMS is a computer-aided system that enables operators of electric utility grids to monitor, control, and optimize the performance of the generation or transmission system. Over 50 years ago, Fred Schweppe introduced the first state estimator to power system operations. Today, it is a crucial function in the energy management system, EMS, as it serves as the foundation for other functions such as contingency analysis, security assessment, dynamic security analysis, and optimal power flow. The state estimator uses the SCADA measurements from substations and the network model to solve for an estimated state of the power system for that time window. The resulting solution is presented to the system operator and used as an input for other functions in the EMS. With the assumed model and parameters, each real-time measurement can be written into a nonlinear mathematical equation called measurement equation. To solve this set of equations, weighted least square algorithm is to handle all the equations together and tries to find the optimal estimate of the bus voltages. This scheme is good when there are only noise or very small errors in the measurements and system model. However, this scheme will reach a biased solution as a sacrifice if bad data are present in the measurements and system model, because the residuals of bad measurements have to be minimized. For example, let us see how a single bad measurement affects the voltage solution and the measurement residuals in weighted least square state estimator. We take a real power system provided by a power company in the USA as an example. The system has 3,409 buses and 4,228 branches. The measurement redundancy ratio is 2.14. Only one bad measurement was added on injection measurement at bus 5. When there is no bad measurement, the solved voltages exactly match the true voltage values. However, this single bad measurement introduced to the injection measurement at bus 5 caused 12 biased voltages and big residuals on 17 error-free measurements. In general, a bad measurement P causes 3 biased voltage solutions, and these 3 biased voltages cause big residuals on 5 measurements, which include 4 error-free measurements, and the bad measurement P. So large residuals imply either error-free measurements or real bad measurements in weighted least square state estimator. When the weight of measurement K is huge, this measurement is actually a leverage point measurement. For a bad leverage point measurement, huge weight forces its residual equal to 0, otherwise, the objective function will have a big value. However, the sacrifice of 0 residual is that the voltage solution is biased. Because power system state estimation is a non-linear problem, the popular bad data detection algorithm, largest normalized residual test, may fail when the largest residual takes place on an error-free measurement. For weighted least square state estimators, big residuals do not imply the corresponding measurements are bad measurements, while small residuals do not imply the corresponding measurements are error-free measurements. Therefore, it is very hard to detect bad measurements for weighted least square state estimators. Today, a widely accepted and efficient bad data detection algorithm is still not available for weighted least square state estimator after more than 50 years. In general, when bad data are present, WLS state estimator reaches a biased voltage solution, has difficulty to converge with severe bad measurements, cannot reject bad measurements, leverage points disable its bad data detection, cannot recover the bad measurements, is prone to diverge, sensitive to bad measurements, sensitive to topology errors, sensitive to parameter errors, and it not originally designed for the application of power system state estimation. To solve all the vulnerable problems suffered by weighted least square state estimator, SE Plus utilizes a different scheme. That is, all the measurements are divided into 2 groups, a basis set called ZB and a redundant set called ZR. A basis set ZB is formed by a minimum number of measurements which is able to solve the entire system. That is, the number of measurements in ZB is equal to the number of variables we have. Obviously, there are a large number of different basis sets ZB, but each basis set can solve the entire system. Assume the measurement I plus 3 in ZB is a bad measurement. For this case, the bad measurement I plus 3 in ZB causes biased voltage solutions at buses 2, K plus 1, and T plus 3. These biased voltages will result in big residuals on multiple measurements in ZR because the recovery of those measurements using these three biased voltages. If the bad measurement I plus 3 is replaced by an error-free measurement P plus 2 in ZR, the error-free measurements in ZR that originally had big residuals due to the biased voltage I plus 3 will now have small residuals because the originally biased voltage solutions now become accurate. In other words, when all the bad measurements are in ZR, and there are no bad measurements in ZB, the voltage solution obtained by ZB will be accurate, and the number of large residuals will be minimized because all large residuals in ZR will only occur on real bad measurements and not on error-free measurements. This is actually the goal of SE+, which is to move all bad measurements to ZR. The objective function of SE+ implies that there is always an optimal basis set ZB that can solve the entire system. By listing all possible ZB sets, we can calculate the residuals of their corresponding ZR sets for each voltage solution. We can then count the number of large residuals and find the minimum one among them. The corresponding ZB set with the minimum number of large residuals is our solution. Massive numerous numbers of tests have been conducted to verify the accuracy of the voltage solution obtained by SE+ and 100% guarantee of convergence. Here we show a test on a real case provided by a power company in the US. The system information and measurement configuration were provided, and SE+ took 0.19 seconds to complete the calculation on a Dell Inspiron 7502N1. SE+ obtained smaller residuals for voltage magnitude measurements compared to the customer's weighted least square state estimator. To make a better comparison, the voltage measurement residuals for SE+ and the customer state estimator were sorted and compared. SE+ reduced the voltage measurement residuals by 34.98%. It shows that SE+ is able to obtain a more accurate voltage solution because the scheme of SE+ pushed the bad measurements to the redundant set ZR, which has no impact on the voltage solution. We also compared the residuals of real power and reactive power measurements between the customer's weighted least square state estimator and SE+. It was observed that due to the accurate voltage solution, SE+ obtained smaller residuals for both real power and reactive power measurements. Especially, SE+ obtained much smaller residuals for reactive power measurements than weighted least square state estimator. Because of the novel algorithm scheme, SE+ is able to reach an accurate voltage solution, easy to converge when severe bad measurements are present, can effectively reject bad data, remove the influence of leverage points on bad data detection, can recover the true values of bad measurements, guarantee 100% convergence to a solution, insensitive to bad measurements, insensitive to topology errors, insensitive to parameter errors, and specifically designed for the applications of power system state estimation. Furthermore, SE+ is much faster in calculation than weighted least square-based state estimators. The CPU time used by SE+ for different systems is shown in the figure. For WLS regression, it is optimal when measurements have noise or very small errors. It obtains biased solution when there are bad measurements or errors in the system model. It cannot reach a solution if the bad data are severe. It is not originally designed for the applications when bad measurements are inevitable, like power systems state estimation. For SE+, it is designed for the applications with bad data. It can effectively reject bad measurements and recover their true value. It guarantees 100% convergence whenever the system is observable. It is robust. SE+ is an ideal offline backup state estimator for power system operations.